Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hamzah Azibi Azman. My metric number is MA20046. I am group leader from Group9. Want to present about the project was given by Dr. Farzad. The project sound about a new power plant is going to be constructed to supply electricity for Kuantan. The power output of this power plant is going to be 50 megawatt. The energy which is being used to increase the temperature of the working fluids come from the burning of coal. The coal has a heating value, energy released when the fuel is burned, of 39,300 kilojoule. The question 1 sound about gas power plant, assuming the turbine inlet temperature is 1000 K. The compressor and turbine have an isotropic efficiency of 95% and 85% respectively. So before we go further, I want to explain a little bit basic of gas power cycle. Gas power cycle have three types. First, Otto cycle, diesel cycle, and Brayton cycle. So the suitable for the question 1 from the three type of gas power cycle, we can use the Brayton cycle because it was competitive to use it. So the Brayton, what is the Brayton cycle? The Brayton cycle is used for gas turbines only where both the compression and expansion process take place in rotating machinery. So the Brayton cycle is suitable to use it. So this is a standard Brayton cycle, and then this is a PV diagram and TS diagram. Before I start the calculation, I need to explain about this cycle. All four process of the Brayton cycle are executed in the steady flow device, so they should be analyzed as steady flow process. Next, when the changes in kinetic and potential energy are neglected, the energy balance for a steady flow process can be expressed on a unit mass basis. Lastly, the thermal efficiency of an ideal Brayton cycle depend on the pressure ratio of the gas turbine and the specific heat ratio. So here is the calculation how to solve the question 1. So before we begin, there some of information that not given, so that I must assume for the temperature 1 at a compressor, because the turbine have given the temperature about 1000 K. So the compressor did not have a temperature, so I assume that the compressor is 300 K, and I assume the pressure of the air is 10, and then normal, assuming the turbine inlet 1000 K, the compressor and the turbine have an isentropic efficiency of 95% and 85%. Alright, so the firstly is we must solve the process 1 until 2, the isentropic compression of ideal gas. So T1 we assume that 300 K, and H1 we get 300.19 kilojoule, and PR1 we get 1.386. Where can I get this information? I get this from the table A17. So from the information that I collected, so I easily to use the Brayton cycle formula to get PR2. So formula is P2 over P1 times PR1. We can easily to calculate 10 times 1.386, we get 13.86. So from the new information was given, we must find the H2. So how we want to find the H2? So we use the information 30.86 to get the H2. So we use also same the table S17, but we use the interpolating system. We use like compare it to get the H2. We use just simple mathematical calculation, and we get the 579.86 kilojoule. So the next process is process 3 until 4. Process 3 until 4 is just use the same method from the process 1 until 2. So for this time is turbine inlet is 1000 K. So there are different information, and we collected from the A70 table. So H3 we get 1046.04, PR3 we get 114. So how do we get the PR4? we just use different formula because the previous is we must time the pressure A ratio, but this time we divided, so we get 11.4. So the 11.4 we just use the same method previously to get H4, and we get 548.79. After we collect the H3 and H4, H2 and H4, we need to calculate W net before we calculate the thermal efficiency. W net, the formula W net is H3 minus H4 minus H2 minus H1, but this time we have the condition that was given the isotropic efficiency 95% and 85% for compressor and turbine. So we must add on the isotropic to the W net. So it will sound like 0.95% times H3 minus H4 minus H2 minus H1 and divided 85%. And we easily use the simple mathematics again. We get 143.37 kilojoule per kg, and we automatically easily to get a mass flow rate. W net, the formula is W net or divided by W net out. So W net out we use 50,000 kilojoule divided by W net we got previous, and then we get a 348.75 kilogram per second. And then the next is how to find the thermal efficiency of the cycle. So we just use W net we get previous. So we just use formula W net over Q in. So W net we just only got from previous. So we must find the Q in. The formula Q in is H3 minus H2. So we just divided simple mathematics, we got 30.8%. And then we calculate the bed ratio. The bed ratio is formula H2 minus H1 divided by H3 minus H4, and we get a 0.562. And the heat required we can get easily because we have got all for information to calculate. So heat required work divided by thermal efficiency. Work we got from 50,000 megawatt from the question, and then the thermal efficiency is 0.308, and we get 162.34 kilowatt. And the lastly is amount of coal required. So we just use a formula 162, where we got 162 from the heat required. So 162 divided by 29,300 kilojoule, so we get 5.541 kilogram per second. So the disadvantage and advantage about Brayton cycle. First, I want to explain briefly about the advantage of Brayton cycle. First, high speed can be obtained. Second, lower operating cost. Third, maintenance charge are low. And lastly, can be started quickly. And then the disadvantage, firstly, temperature of combustion chamber is too high, thus resulting in a lower life. Second, most of power is used drive to compressor, so it gives less output. And then lastly, overall efficiency of turbine is low because the exhaust gases contain most of heat. Alright, so the question 2 is sound about a vapor power plant, assuming that 80% of the energy is transferred to steam in the boiler. So easily I can know about the question 2. We can use the Rankine cycle. So before we start the Rankine cycle, we must assume that there is isentropic compression S2 equal to S1 and expansion S4 to equal to S3. And then standard model boiler and condenser are constant pressure device. And lastly, P3 to P2, I assume that using 5 megapascal, and P4 and TP1 I use 25 kilopascal. So this is a Rankine cycle diagram. So the Rankine cycle diagram from 1 to 2 is isotropic compression in a pump. So what is 1? 1 is water enters as saturated liquid, and 2 is water compressed to operating condition for boiler. And then 2 to 3, constant pressure heat addition in a boiler. 3 to 4, isotropic expansion in a turbine. So what is 3? 3 is a water lift boiler as superheated vapor. And lastly, 4 to 1, constant pressure heat rejection in a condenser. So the 4 is vapor expand and steam enters the condenser. So this is a TS and PV diagram as we know. So we can jump to the next part. Is the best part is the calculation. So the calculation not little bit, is far different from the Brayton cycle. So the Rankine cycle, we not use the A17 like previous calculation. We use A5 table A5 at pressure 25 kilopascal, and then we get H1 at HF at 25 kilopascal, we get 271.93 kilojoule. S1 we get at 0.8931 kilojoule. V1 we get at 0.001020 meter cubic. So how I want to find at the location 2. So from the location 2, we can use to express the reversible work in a shown in equation 2. The liquid H2O can be assumed to be an incompressible substance. V1 equal to V2 equal to V. So we just combine equation 2 with equation previous and isolate for the H2. Equation 12 is obtained as we see the substituting the known values into equation 12, H2 can be determined. So we just put the information that we get from the table, and then we get 277 for the H2. So the next is we must find 5 megapascal for T1000. Why we use A6 not A5? Because the temperature and at location 3 are known to the properties can be determined from the steam tables. Looking in the table F5, it observed that the corresponding saturated temperature is 263.95 Celsius. Since the temperature at location 3 is greater than saturated temperature, the steam must be superheated. So I use the table A6 with pressure 5 megapascal, the temperature is 1000. Easily I get the information H3 and S3. So H3 is 4328.3 kilojoule, and S3 I get 1.1648 kilojoule. So this is best part is S4 equal S3. S4 is same to S3. We just use same as amount, value of amount. So the next is we must find the X4. So X4, the formula is S4 minus SF divided by SFG. Easily we get at 1.0482. So the next is we must find the 25 kilopascal at table A5, because the enthalpy at state 4 can be determined by interpolating using the quality between the saturated liquid and vapor states at P25 in table A5. So H4, we just use formula H4 at P25 kilopascal plus SXHFG at 25 kilopascal. We get 271.933 plus 1.0482 times 271.93 plus 1.0482 from X4 we get previously, and then times 2345.5, and we get easily 2730.48 kilojoule per kilogram. So when people ask me where can I get this information, all of this, first we must know the formula, and we must know read the table. So we easily get the information that we can get the H4 is 2720.48 2730.48 kilojoule per kilogram. So we got all the information to get to find the thermal efficiency. So we got H4, we got H2. So H1 has been stated and the H3 also has been stated. So the formula, the thermal efficiency can be calculated by substituting the valve of H1, H2, H3 and H4 into the equation 10. So the formula is 1 minus bracket H4 minus H1 bracket divided by H3 minus H2. We easily get 0.435 and change to the percentage. We get a 43.5%. So the question 2 was given that 80% of turbine inlet. So the information was given we can use to find the overall plant efficiency can be obtained by substituting the valve or the thermal efficiency into equation this. So the N overall and com times NTH times Ngen. So that means it's sound about 0.8% from the turbine, 0.435 from the we got from the thermal efficiency previously we got that, and then times the 95% that I assume the pump for inlet. So easily we get 33.06%. So the lastly is how to find the coal. So the rate of coal supply can be determined by substituting in the net electric power output 50 megawatt. So the heating of coal is 29,300 kilojoule. So the overall efficiency is we got from the previous we calculate together is 0.3306. So we just use simple mathematics. 50,000 divided by 29,300 times 0.3306 and we get 5.16 kilogram coal per second. Alright, the lastly is I want to explain about the advantage and disadvantage. So the advantage for the Rankine cycle is it improves the thermal efficiency. The next is it increases the network output, and then lastly it reduces the steam rate per kilowatt. For the disadvantage is the first one is to increase the cost and size of plant due to inclusion of reheater and its long piping, and the lastly is increase the size of condenser based on the unit mass of the due to improve quality of system exhaust from turbine. So what I can conclude from the question 1 until 2, we must know what we use the formula for breaker, I mean the gas power plant and vapor power plant is totally different, and then we must know the table about the gas. Thank you.
Assalamualaikum and very good morning to Dr. Farzad and my friends. Okay, today I will talk about combined steam power plant. Okay, and this picture shows how to build a power plant cycle based on combined steam. Okay, next. Okay, this is my TS and PV diagram for combined gas and vapor power plant. Okay, at the left side we got TS diagram, and the right side is PV diagram combining to get from Rankine and Brayton cycle. Then we got our diagram. Okay, for our conclusion for the question, I take some of the point from my friends question from 1 and 2 question from the Rankine and Brayton. Okay, from the gas cycle, I make H4 from the H3 minus H3 minus H4 to get the work net out, and then I take Q in and also total work net, and assume new H5, and then from the vapor cycle I take point at H2, H3, and also work net. I make a new one work net since my friend's Rankine cycle did not use this specific formula to get work net, so I use it work net equal to Q in minus Q out and get the work net. Next, this is how I get a new mass flow rate for Rankine, since Rankine didn't have any mass flow rate yet. So yeah, and also I use this to get total network to get the Y. So I use the formula total work net equal to work net gas plus work net vapor. So I get 185.01 kilojoule per kg. And also for the thermal efficiency that the question need, I got efficiency 0.40 or 40%. Then for the next question, it want amount of core required. So since I don't have heat required yet, so I use heat required work over efficiency. So I got 125 kW, and amount of core required 125 divided by 29,300, and I got 4.266 kg per second for the core required for this gas vapor cycle. So for the next is advantage and disadvantage for having gas vapor cycle. So the advantage of having this cycle is we can use less coal, since the coal used at the burner rotating to each of the cycle, so it improve overall efficiency. But for the disadvantage of making this power plant is cost to build is very expensive, and also it less responsive to power demand. And for the conclusion of our project is every power plant have their own advantages and disadvantages, as I said, and then we can learn more about this cycle through our project. And then last but not least, I think gas vapor cycle is more effectively used in our factory, so we can get most of it. Okay, that's all for me. Thank you very much.